For an object to undergo circular motion, it has to be traveling on a circle. Here you see the point P. P is traveling at a constant velocity around the circle. But exactly how fast is P traveling? We know that velocity is equal to the distance traveled divided by the time. So, the velocity of P is 2 pi r meters over the period. But how does an object even manage to stay on a path like this? If there's nothing affecting the object, then we know that the object will be traveling in a straight line, as per Newton's first law of motion. So, there has to be a force pulling this point P towards the center of the circle in order for it to maintain the circular path as it goes around. This force is called the centripetal force. The centripetal acceleration is given by the formula AC equals v squared over r. We know that the normal force, Fn, equals the mass, 2000, times acceleration of gravity, which is about 10. The frictional force is equal to the normal force times the coefficient of friction, which equals 14,000 newtons. Then centripetal force also equals the mass of the car times the centripetal acceleration, which we saw up here equals v squared over r. And then we get v equals 8.4 meters per second. So 8.4 meters per second is the maximum velocity you can take this turn successfully at. Let's draw a quick diagram to help us out here. So, if the force of gravity is pulling down here, with some force Fg, if this is less than the centripetal force, then the car will stick to the track and make it all the way around. If the force of gravity is greater than the centripetal force, then by the time it comes up here, the cart will be pulled off by the force of gravity and fall down, and it will not make the turn. The centripetal force is equal to mv squared over r, which equals about 1400 newtons. This is our centripetal force. Our force of gravity here, Fg, equals 2500 newtons. We know that the cart will not make it. Isaac Newton came up with an equation to calculate the forces caused by this force of gravity. This is where g is the gravitational constant, which is a really small number. m1 and m2 are your masses of the two objects, and where r is the distance between the two objects. If you want to put something in orbit, we need the force of gravity to equal the centripetal force. In that case, Fc equals Fg. Here we're assuming that m1 is the mass of the object that's orbiting around the larger one. So we can simplify this a bit. So we get v equals the square root of gm2 over r. G, the acceleration of gravity, equals gravitational constant times the mass of the planet all over r squared. We just plug in these numbers into this formula right here, and this gets us v equals 3 meters per second. A key thing to notice here is that in neither the velocity nor the gravitational acceleration equations does the mass of the satellite matter. The only masses that are taken into consideration is the mass of the planet. Here, we start with writing out our velocity equation. In this case, g is a constant, so it stays the same. m1 is the mass of the Earth, and r is the radius of the Earth plus the distance above the surface, which in this case is 6,500 kilometers, or 6,500,000 meters. At this point, it's simple. You get that the velocity is equal to about 7,800 meters per second, which is